Some time ago, I wanted to create my own low-cost digital thermometer to stick on the window of my home. The initial idea was that it would not only have temperature information, but also atmospheric pressure, and that it would present a daily report on the device display. And so my journey to design the device has just begun. Initially, I was going to use the Bosch BMP180 sensor, since I had some sample of this sensor on hand. It is a 2-in-1 device with a temperature sensor and an atmospheric pressure sensor on the same die. The microcontroller would be the popular STM32FE103C86. But due to the global chip shortage, it was too expensive. It would exceed the project budget. That when I came across the STM32G030F6P6. It is extremely cheap chip with lower power consumption and is much smaller compared to the previous one. It was perfect for my project. The next step was to choose the display for the device. I spent a few days searching AliExpress for a display that met my requirements. The goal was to have a transparent screen, similar to the one in the picture on your screen now. It commonly found on AliExpress. However, it won't be a 7-segment display, but rather a COG, chip-on-glass display, which is known for allowing pixelated images to be displayed. To meet the transparency requirement, I needed a specific type of LCD that would allow me to see through the other side. For this, I needed to choose an LCD with the correct polarization. There are basically three basic types of LCD polarization: reflective, transflective, and transmissive. Transmissive, that was exactly the type of polarization that I would need. The challenge now was to find an LCD display that meets these requirements on AliExpress. I confess, it was not an easy task. Sellers usually do not put all the technical characteristics in the product description. There are even cases where the product has no description at all. After a few days of searching, I finally found this model. The description said it was a COG display with a transmissive polarization. The chip was the ST7567, and looking at its datasheet, I saw that it was very easy to program and, best of all, had low power consumption, around 200 microamps when turned on. The next component on the list is the battery. I opted for the CR2032 standard. I bought not only the battery, but also the adapter for it to fit on the PCB. While the components were not yet delivered to my home, I spent my free time designing the PCB schematic and the device's case. It was my first time using Kicad, and I didn't know anything about it. My challenge in the next few days was to learn how to use Kicad. I realized that it's a very easy to use software, in addition to being free and open source. I downloaded the necessary libraries and completed the design of my PCB. The next mission was to model the case of my thermometer. For this, I used another free and open source software, Blender. The biggest difficulty I encountered was calibrating the dimensions of parts with the dimension of the PCB. However, after some printing and calibration, I arrived at the correct dimensions. And finally, the components from China arrived. One of my first tasks was to remove the back parts of the display that reflect the backlight. Soon after, I printed the circuit on a photographic paper and then did the thermal transfer to the PCB in a process I like to call thermolithography. And then came the part that would change the course of the project. the soldering of the components. I have some experience with the SMD soldering with a soldering iron for some time. So I soldered the LCD, the STM32, capacitors, resistors, button, but when it came time to solder the BMP 180, the project took another direction. I was so excited about Kicad that I forgot I need to make the pads of chat wider. In previous projects, I was successful in soldering with a soldering iron using wider pads. However, in this project, I was careless and only realized the mistakes during soldering. I tried to solder it and ended up damaging some trace on the PCB. I was extremely disappointed, and in order to not lose the work, I decided to change the direction of the project. I need to think of something that would adapt to this PCB, and that's how the idea of the Chrome T-Rex Dino pocket console came about. In the following days, I started to develop the firmware of the mini console. I tried to make it as faithful as possible to the original game, but adapted to the limitation of the project. I simplified some things to fit the new project, which now was called T-Rex Dino Pocket Game. I printed the final case, screwed the board onto it, and here's the final result. I must admit, it was difficult to see the game obstacles due to the LCD latency and also because it was transparent. And before I forget, the final cost of the project was around $5. Don't forget to subscribe and leave your like, and see you in the next project.